Hello, welcome to another video of Thermodynamics 2. In this video, I'm going to explain the second law of thermodynamics. First of all, we're going to look at what the thermal reservoirs are. Thermal energy reservoirs are the bodies that can absorb or release infinite amount of energy without changing its temperature. For example, that kind of bodies are lakes, rivers, atmosphere, probably a large surroundings like a large building, something like that. That's also atmosphere. Um, and ocean. These kind of things can be considered as a large thermal energy reservoir. So they can absorb more, uh, any large amount of energy without undergoing a significant temperature change. The second thing that we look at is a heat engine. Heat engines is the most important thing at the onset of industrial revolution, where people were looking for means of converting heat to work. Heat cannot be converted to work directly, although work can be converted to heat directly. So the device that we use to convert heat to work is named the heat engine. And there are four common characteristics of heat engines. They usually receive heat from a higher thermal energy reservoir and convert a part of that energy or heat to work. And they must reject the remaining heat to a lower thermal energy reservoir. And they must operate on a cycle. There should be cyclic devices. Now, the efficiency of a heat engine can be computed by using 1 minus Q out over Q in. This can be easily taken by the general efficiency equation is named desired output. I really like this definition, and required input. So what is the desired output? Desired output in the heat engine is the net work output. So I put W dot net, W net out. And the required input is, this is what is required, Q in, right? Q in, not net Q in, but Q in, okay? So by taking this entire thing as a system, right? As a system, and it's actually a cyclic device. So when you go on a cycle, right, I can write the first law of thermodynamics for that cycle. I'm just going to demonstrate how you got this one. I'm going to write that first law of thermodynamics. This is a closed system, right? Because there's no mass interactions here. There's only heat and work interactions, right? There could be mass interactions, the actual inside cycle, but I can take the cycle, the complete cycle, as a collective closed system. My surroundings is outside, this lower energy thermal temperature, thermal reservoir, and then high temperature reservoir. So you have delta U is equal to Q uh, net in minus W net out. Okay. Now, when you put on the cycle is a sequence of thermodynamic process that starts and ends at the same state. So let's say it started at state one. So it started at state one and ends at state one. So it's U1 minus U1, which is 0, right? Equals to net in minus W net out. Now then W net out is equal to Q, I shouldn't put dot, I'm not considering rate equation, Q net in. So what is Q net in? Q net is net in is Q in minus Q out. So I can substitute for W net in here, net out here. That's Q in minus Q out and divided by Q in. And that's 1 minus Q out or Q in. Now, this heat engine could be a steam power plant. This heat engine could be a automobile engine. This heat engine could be a gas turbine plant. And either can be considered as a closed system and open system if you got individual components. But now we have encircled the entire plant or entire engine. So then it again be considered as a closed system where you would see only heat and work interactions. You don't see any mass interaction. So that's why we consider that as a closed system. So I just wanted to emphasize that fact in here, because I may be using that over and over again. So there's a problem here. A heat engine receives heat from a heat source at 1200 degrees Celsius and rejects heat to a sink at 50 degrees Celsius. The heat engine does a maximum work required to maximum work equal to 500 kilojoule. Determine the heat supplied to the heat engine by the heat source and the heat rejected to the heat sink. So we have a heat source at 1200 degrees Celsius, and it's applied to a heat engine, which is shown like here. And this is the work out, right? Maximum heat, maximum work, right? Net out, maximum, max, 500 kilojoule. And it rejects to a heat sink at 50 degrees Celsius. Okay. And this works on a cycle, right? And if it outputs a maximum work 500 kilo equal to 500 kilojoule, it should have its maximum efficiency. So for heat engine, the maximum efficiency is known as Carnot efficiency. That is 1 minus TL over TH. TL is the lower thermal reservoir temperature at in Kelvin scale, and TH is the higher thermal energy reservoir temperature at in Kelvin scale. So it's 1 minus 50 plus 273 divided by 1200 plus 273 maximum, right? So that maximum efficiency is 1 minus, this is 323 divided by 1473. So by solving this part of the equation, we can find 1 minus 323 divided by 1473. It's 0.781, right? So when it operates at this maximum efficiency, it outputs maximum work. So we can say that in the thermal efficiency max also equal to 1 minus, sorry, uh, W net out max divided by Q in. So Q in is equal to W net out max, that is 500 divided by 0.781, right? So that will give you 500 divided by 0.781, 640 kilojoules roughly, right? So and then you know that from the first law of thermodynamics, I can apply first law of thermodynamics for this entire system, right? For the cyclic process, it's going to be W dot net out is equal to, sorry, that's not dot, equals to Q in minus Q out. So Q out is Q in minus W net out. Q in is 640 minus 500. This is 140 kilojoule is heat out. That's how you get this solution for that. Okay, so we got Carnot efficiency. This is called Carnot efficiency. Right. And then there's a statement about second law of thermodynamics that's called Kelvin-Planck statement. You saw that there must be a heat sink for a heat engine to generate a net amount of work. So Kelvin, Lord Kelvin and Max Planck combinedly uh, stated this: it is impossible for any cyclic device to receive heat from a single thermal reservoir and produce a net amount of work. There must be a heat sink. There must be a place to uh, reject the heat. Otherwise, it wouldn't work. So that means you will never get 100% efficiency of a heat engine. The maximum efficiency is given by the Carnot efficiency. For refrigerators, we defined coefficient of performance, that is the desired output divided by required input. Desired output for refrigerators is it's also cyclic device is the cooling load or the heat supplied or heat rejected by the cold space. Now this is an unusual thing because what we're seeing here is heat is transferred from a colder space to a warmer space. Does it happen spontaneously? No, it doesn't. That's why we need a work input, right? So work input is required to make this process happen. Otherwise, there's no way that we can transfer heat from a cold thermal reservoir to a warm thermal reservoir, or lower thermal reservoir to higher thermal reservoir. Heat transfer wouldn't take place spontaneously. It requires a device. It requires a work input. So that's why this coefficient of performance is defined like that. And for heat pumps, does the same thing, but the uh, desired output is, in this case, actually not the desired output. Is the This is the desired output. The desired output is still QH for this case, so that's why heat pumps is defined like that. So still in this case also you can apply the first law of thermodynamics for this cycle. You get delta U equal to 0. So delta U is equal to W dot net, sorry, uh, you get Q dot Q in minus W Q in, sorry, Q uh, in minus Q out minus W out minus W plus W in minus W in. So that is 0, and then we get this is net out, and I can move that into this side. W dot out, W dot in equals Q in minus Q out. Okay, and this can be written as minus W net in equals Q in minus Q out. And here Q in is QL, right? Q out is QH. So that W dot in. So you have W net in, if you multiply both sides negative sign, QH minus QL. And then you can substitute there, and you get COP of R QL divided by W net in, which is nothing but QL divided by QH minus QL. You can divide it by QL entire equation, 1 divided by QH over QL minus 1, COP of R. And for this case also, we can use the same first law of thermodynamics and apply this equation and obtain this equation like we did in previous refrigeration cycle. The closest statement is for heat pumps and refrigerations. It says it is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a lower thermal temperature body to higher temperature body. That means you cannot construct a cycle. You cannot construct a cycle which transfer heat from lower thermal reservoir to higher thermal reservoir. This cannot be constructed. You need to have some kind of input. You need to have some kind of input, that is the work input that you put into your refrigerator and heat pump. So this is E of L, and you need work net in. Some network output must be there for this cycle to operation. Okay. And we discuss some processes called reversible processes. Reversible processes are processes that can be reversed without leaving any traces on the surroundings or on the systems. So reversible process is devoid of friction, and it doesn't have finite amount of heat transfers. There are different reversible systems, reversible processes are defined, you uh, might have done this in Thermo 1. Why are reversible processes important? Because when a cycle is built built by all the reversible processes, then that cycle or that heat engine has its maximum efficiency, or that refrigeration system has its maximum coefficient of performance. For example, we have here a Carnot cycle and a reverse Carnot cycle. Carnot cycle is comprised of 4 reversible processes. 1 to 2 is reversible isothermal expansion, and 2 to 3 is reversible um, isentropic uh, expansion, and you have a reversible isothermal compression, and then we have reversible isentropic expansion. So these are the complete reversible cycles. So whenever a heat engine operates on a complete reversible cycle, that heat engine has the maximum efficiency in between a given set of thermal reservoirs. For example, if you have a thermal reservoir is a TH, let me draw it a little bigger. We have a thermal reservoir of TH and TL. Let's say this is your uh, engine inside temperature, and this is the environment temperature. You devise a heat engine that is not consist of reversible, let's say it's an irreversible heat engine. It draws some energy and produce work and rejects heat. And you also have a reversible heat engine which comprises of all the reversible processes, right? And this is Q in, Q out, Q in, Q out, work net out, work net out, right? So this efficiency of reversible is always greater than or equal to the efficiency of irreversible in between the same thermal reservoirs. So if you have 2 reversible heat engines operating between the same thermal reservoirs, they have the equal efficiency. So if you have one of the examples is Carnot cycle, and these are called 2 Carnot principles. Okay, the efficiency of an irreversible heat engine is always less than the efficiency of a reversible one operating between the same 2 reservoirs. The efficiencies of all reversible heat engines operating between the same 2 reservoirs are the same. Okay, and for reversible heat engine, Carnot cycle efficiency is known as 1 minus TL over TH. Carnot cycle coefficient of performance is 1 for refrigeration is 1 over TH over TL minus 1, and this is 1 over 1 minus TL over TH for heat pump. And this is the second problem. An inventor claims to have devised a cyclical engine for use in space vehicles that operates with a nuclear fuel generated energy source whose temperature is 920 Rankine and sink at 490 Rankine that radiates waste heat to deep space. He also claims that this engine produces 4.5 horsepower while rejecting heat at a rate of 15,000 BTU hour. Is this claim valid? Okay, is this claim valid? Let's see, how do you find whether this claim is valid? So based upon the Carnot principles, right? let's say you have a reversible engine that should have the maximum efficiency, and reversible engine is not practically possible. But anyway, if he created a reversible engine, its efficiency should be maximum. So the maximum efficiency that he can attain in between those two given uh, thermal reservoirs, one is at 920 Rankine, the other one is at 490 Rankine. Sink in, this is TH, this is TL, and that's the engine network. So maximum efficiency that he can obtain within these two thermal reservoirs can be found by 1 minus TL over TH. So we can, Rankine temperature can be used instead of Kelvin temperatures because it's a thermodynamic temperature scale. 1 minus 920, 490 Rankine divided by 920 Rankine. So we have 1 minus 490 divided by 920. That's 0.467 efficiency, right? That's the efficiency. Now let's find out his claim about that it Q out, right? Q dot out is 15,000 BTU per hour, and it produces net work, net out 4.5 horsepower. If you convert the horsepower into BTU per hour, right? There's a conversion factor table in the back of your book. So horsepowers to BTU hour is 1 horsepower equals 1 horsepower equals 20, 25, 44.5 BTU per hour. So this network output is W net out is 4.5 times 25, 44.5 BTU hour. So we have heat rejected but to find the efficiency, we need heat in. By applying our first law of thermodynamics, as I showed earlier, I can write W dot net out is equal to Q in minus Q dot out. Okay. So then you can find Q dot in is equal to W dot net out plus Q dot out. That will give us this is 15,000 plus 4.5 times 25, 44.5 plus 15,000. That's 4.5 times 25, 44.5 plus 15,000. That's going to be 26,450. 26,450 BTU per hour. Now the actual efficiency, this is reversible efficiency. This is thermal efficiency actual. W dot net out divided by Q dot in. So we have 4.5. So W dot net out, this is 4.5 times 25, 44.5 is 11,450. 11,450 0.25. So you have 11,450 divided by 26,450. So let's calculate that divided by 11,450 divided by 26,450 is 0.43, 0.43, 0.433 efficiency. So this efficiency is less than this efficiency. So we can say that I'm going to write it here on top because I'm running out of space. So the actual efficiency, actual, eta actual, thermal actual less than eta thermal reversible, theoretical. Therefore, the claim is, his claim is correct, is valid. Claim is valid. Okay. That's how you deal with that kind of problem. So first we find the uh, uh, the theoretical efficiency, and then we find the actual efficiency and compare them. If you get actual efficiency is greater than the theoretical efficiency or the reversible efficiency, then that is not possible. The problem number 3, a refrigerator operating on the reverse Carnot cycle has a measured work input of 200 kilowatt and heat rejection of 2000 kilowatt to a heat reservoir at 27 degrees Celsius. Determine the cooling load supplied to the refrigerator in kilowatt and the temperature of the heat source in degrees Celsius. Okay, so it is operating on a reverse Carnot cycle, so it is a perfect thermal reservoir. Reverse thermal reservoir, and sorry, perfect refrigeration cycle. I'm sorry, and we can draw such a cycle. We have TH, right? TH is unknown, and we have uh, the cycle rates on, and you have a work input W dot net in, and you have Q dot L, that's the lower thermal reservoir, and this is Q dot H, and this is TL equal 27 degrees Celsius, that is 300 Kelvin, right? 300 Kelvin. And we need to find this cooling load supplied to the refrigerator. And measured work input is 200 kilowatts, and QH is 2000 kilowatt. QH is 2000 kilowatt. Now we can easily determine Q dot L by taking this entire cycle as a closed system. It's a cyclic process. So you have delta U equals Q dot in minus Q dot out plus W dot in minus W dot out, right? Or we can say that we take that closed system equation, Q dot net in minus W dot net out. Okay. Net in, so delta U is 0. Why? Because it's a cyclic process. Since it is a cycle, delta U equals 0 because it starts and ends the same state. Sorry. 0 is equal to and then this is net in is whatever in, that's q dot L minus q dot H, right? And whatever out, net out, there's no net out, there's no net and there's no out, but there's an in, so I can put W dot net in, okay, W dot in. So this gonna be I need to find q dot L, which is q dot H, right, minus W dot net in. So we have 2000 kilowatt minus 200 kilowatt, 2000 minus 200. Yeah, so we have 1800 kilowatt q dot L, and it's on a, it's in a reversible cycle, so we can find the COP of R. Desired input is q dot L, so we have q dot L divided by required input is W dot net in, which is 1800 divided by 200, it's 9. COP is 9. Okay, and that's also reversible COP. So reversible COP is COP reversible, refrigeration reversible is 1 divided by TH over TL minus 1. So we have this equation written here, reversible TH over TL minus 1, TH over TL minus 1. It is given that this is work on a Carnot cycle, so the one that we calculated 9 is equal to this. So we have 1 over TH, we don't know, TL is 300 minus 1, and we can solve for TH. TH divided by 300 is minus 1, so y equals minus 1 equal to 1 over 9, right? And then TH equals 1 over 9 plus 1 times 300. So we have, this is 10 over 9 times 300. 3000 divided by 9, TH, that's in Kelvin. So 3000 divided by 9, 333.33. Minus 273, you get 60.33 Celsius. So TH actually, let me write it like here, 333.33 Kelvin. That is TH in Celsius, it is 60.33 degrees Celsius. That's the answer. So that's the first answer, QL, and this is the second answer. With that, I conclude this video. And if you have any questions and concerns regarding the second law of thermodynamics or these problems, please get in touch with me and ask more questions in the class. Thank you very much for watching. See you in the next video and in the class.